We will conclude section 6.1 by discussing several applications. The first application that we'll be working with is finding what is called arc length. Our definition says, given a circle of radius r, the length s of the arc subtended by a central angle theta is given by, and we have our formula. To simplify things, let's be sure that we understand what it is that we're finding when we find arc length. So we have a circle, and we have an angle inside that circle. The distance from the point where the angle on the initial side intersects the circle, so from here to the point where the terminal side of the angle intersects the circle. This distance in between these two black dots that I just drew, that is the arc length. So in other words, it's the distance from walking from this point along this outside edge line all the way to that point. And you can see that that is denoted by the S. Now, as far as our formula goes, our formula that we're going to keep in mind as we start to work problems is S is equal to R times theta. This part in the middle of our formula just simply gives us some idea of where that formula comes from. But for the case of working problems, we will simply use S is equal to R theta. R is going to be the radius of the circle, and theta is going to be the angle. Now, the one criteria that we really need to be careful about is that this formula requires that the angle be in radians. So if you remember in an earlier lesson, we discussed the fact that sometimes we have to convert an angle from degrees to radians so that we can use it in an application problem. And this is one of those cases. So you want to make yourself a note somewhere that your angle, theta, has to be in radians. Otherwise, this formula that we are given does not work. Okay, so let's take a look at an example using this formula. I'm going to drop my formula up here at the top so we don't forget it. S is equal to R theta. And let's look at how this is applied. All right, so we are told that we have this island that is here at 90 degrees west longitude, and we have the international date line, which is here at 180 degrees longitude. And we want to know if a ship travels in between these two yellow dots, how far does it travel? And so you can think about the equator of the Earth being like a circle. All right, and we are given the radius of that circle to be 6370. So we know that this is the R value in our formula. Now let's think about our angle. Remember that our angle is going to run from 90 degrees to 180 degrees. So the difference in those two values is going to be the angle that we're looking at. So 180 minus 90 gives me a 90 degree angle. And this is going to be our theta in the formula. Now again, remember that your angle has to be in terms of radians. So we need to think back and ask ourselves, what is 90 degrees in terms of radians? And at this point, we have one of two situations happening. Either you know that 90 degrees is equivalent to pi over 2. That's going to be your best scenario. Or you're going to have to take a minute and convert. So if we have to convert it, remember that you are going to take that 90 degrees and you're going to multiply by pi over 180. And so when you multiply that, you're going to have 90 pi over 180, which is going to equal that pi over 2. Again, having that memorized is going to be faster, but if you need to convert it, then convert it. So you know that your angle is pi over 2, and we know that our radius is 6,370, and so we'll go and plug into our formula now. All right, so we've got S is equal to our radius times our angle And they are going to want this plugged into your calculator to get a number answer that doesn't involve the pi. So we're going to do 6,370 times pi over 2, and that should give us approximately 10,006 kilometers. So you can see that the arc length formula is a fairly straightforward formula. The only stipulation is that you have that angle in radians. Okay, so another application for our angles involves angular speed and linear speed. So this says that if an object moves along an arc of a circle, right, so we're talking about the arc that we just found, defined by a central angle theta and time t, the object is said to have an angular speed omega, given by this formula, omega is equal to theta divided by t. Furthermore, if the circle has a radius of r, the distance traveled in time t is the arc length s, and the linear speed v is given by the formula v is equal to r times omega. Now again, as we get into an example, hopefully we will be able to simplify this and make it make a little more sense than what we get when we read it through the first time. All right, so let's go ahead and take a look at an example and see what we're going to need to do, and we'll come back and get the right formula. So it says, suppose an ant crawls along the rim of a circular glass with radius 2 inches. So the ant is crawling around the top of the glass and traverses the arc indicated in red below in 20 seconds. So it takes the ant 20 seconds to travel from here to here in the red part of the arc. What are the angular and linear speeds of the ant, and how far does it travel? So we actually have three things that we've got to find. So let's start with the angular speed. So I'm going to go back to my previous slide, and I'm going to get a formula for angular speed. So that formula says that we're going to take the central angle and divide it by the time. All right, so central angle divided by the time was going to give us the angular speed. All right, so what is our angle? So what you want to do here is you want to look at your picture, and again, like we did in the last presentation, we want to compare that back to our unit circle and try to determine the angle. So the angle is the angle that originates here. This is our initial side of the angle that we're looking for, and ends here. So the angle that we're talking about is this angle right here. Now, looking at your unit circle, what angle is that? Well, we know that it's not the angle that cuts this quadrant in half. All right, so we know that we are to the right of that, a little bit less than that. And so you can deduce then that that angle is the angle 2 pi over 3. And you want to realize at this point in our studies, when they have an application problem like this, they're going to be selecting one of those angles off of that unit circle that we looked at in the last presentation. So you want to just compare and find the one that you believe that they've noted. All right, so 2 pi over 3 is our angle, and we know that our time is 20 seconds. And so we're going to plug this in. So I'm going to put a 2 pi over 3 in for my angle, and I'm going to put 20 in for the time. All right, so we are going to write the 2 pi over 3 down, and we're going to multiply by the reciprocal of 20, which will be 1 over 20. So that's going to give me 2 pi over 60, or pi over 30. And if you're looking at your units, we know that the initial angle was in radians and the initial time was in seconds. So we're looking at pi over 30 radians per second. so now we want to look at the linear speed of the ant. So again, I'm going to go back to the previous slide and get my formula for linear speed. Linear speed is denoted by a V, and it's equal to R, which is our radius, times our angular speed, omega. All right, so we know that our radius is 2 inches. They tell us that in the problem, so we can plug a 2 in for the R. And we calculated our angular speed to be pi over 30. So we'll plug that in. And so we're going to have 2 pi over 30, which will reduce to pi over 15. And since our radius is in inches and our time is still seconds, we will have pi over 15 inches per second. And finally, the question asks us to determine the distance that the ant travels. So if we're looking at the actual distance that he travels, we are talking about arc length. And so that is our last calculation here. We're going to find the arc length. Remember that your formula for arc length is S is equal to R times theta. And so we know that our radius is 2, and we know that our angle is 2 pi over 3. And so we'll simply plug those in. And multiplying, we get 4 pi over 3, and our distance is in inches. And keep in mind that in any of these examples, they may ask you to go ahead and write your answer in terms of a decimal, in which case you would want to plug into your calculator. All right, a final example for an application is what is called the area of a sector. And so what we're talking about when we talk about the area of a sector, we're still looking at a circle. So let me draw a circle real quick. And we're still talking about having an angle inside the circle. So we might call this angle theta right here. And remember that your arc length would be this arc here. So if we're talking about the area of the sector, we're talking about the area of this section that's sort of sectioned off by that angle. And we're told that the area is equal to, and again, this part in the middle is sort of the y behind the formula, but the actual formula that we'll be using is r squared theta divided by 2. All right, so let's look at an example. It says that we want to determine the area of the sector defined by the given radii and the angles. And so we're going to take our formula. Again, our formula is A is equal to r squared times theta divided by 2. And again, remember that in order to use these formulas with the applications, your angle must be in radians. So for part A, that presents a little bit of a problem because 52 degrees is not in the right format. So the first thing I need to do is I actually need to convert that 52 degrees. Converting that to radians, remember that you need to multiply by pi over 180. So that's going to give me 52 pi over 180. And 52 over 180 is going to reduce to be 13 pi over 45. So when we go to our area formula for part A, we're going to plug in a radius of 3 centimeters, so it will be 3 squared according to our formula. we're going to multiply that by our angle, which is 13 pi over 45. And we're going to divide by 2. And when we do that, we will go ahead and put this in our calculator to get a decimal for the area of that sector. And when we do that, our area is equal to 4.08. Our unit is centimeters. And remember that anytime you're finding area, then we're talking about a square on the unit. So 4.08 centimeters squared is the area for part A. For part B, we're told that the circle has a radius of 1/2 and the angle is 4 pi over 3. And so this is a little bit easier because I do not have to convert the angle. It is already in radians. So I'm simply going to plug into my formula. I'll put the radius in and square it. I'll multiply by my angle, 4 pi over 3. And I will then divide by 2. And again, I'm going to go to my calculator with this and get a decimal approximation, which would be 0.52. Our unit is feet this time. And remember that area has a square unit to it.